Hello everyone, my name is Tom Patrick and this is a summary presentation of my final year mechanical engineering dissertation, which is on the design of closed-loop inverse kinematic algorithms and their application to the Arduino Braccio. Readily available URDF files proved inaccurate for this project, therefore a custom one had to be created. The CAD files were downloaded off the Arduino website and imported into CAD. This CAD model was then imported into Matlab Simscape and configured for future usage. This custom URDF features far higher quality meshes, CAD accurate link nets and joint positions, which will in turn help with future maths. Braccio in its default configuration features an issue. The default Braccio does not expose motor servo angles. This makes closed loop control impossible. The solution taken was to modify the servos to expose the servo position. A single wire can be soldered to the servo's built-in potentiometer. The arm was disassembled so that each of the 6 motors could be modified. It was then reassembled and connected to the excess pins on the Arduino. Shown here is the servo modifications working. Next, the manipulator could be calibrated using a smartphone. The following equation can then be used to find the real angle. The servos are accurate to the nearest 0.3 to 0.6 degrees. Forward kinematics is the method of finding the end effector position based off all of the joint angles. Forward kinematics is also required for inverse kinematics. Forward kinematics is the product of all homogeneous transformation matrices. Each matrix is constructed using standard building blocks for revolute joints. Multiplying them all together yields the forward kinematic transformation matrix. Inverse kinematics is by definition the inverse of forward kinematics. Given the end effector position, what are the respective joint angles required? This, however, can be challenging for many reasons, such as how inverse kinematics can have infinite solutions. To solve inverse kinematics in this project, a Jacobian matrix was constructed. Shown is the definition of the Jacobian matrix. Essentially, it provides a lookup table of movement magnitude of the end effector when a specific joint is moved. Within this project, it can be computed using known identities for revolute joints, as shown on screen to compute the Jacobian matrix. Inverse kinematics needed a trajectory to track. Basic trig functions were used to create a circular 3-dimensional trajectory that lies easily within the manipulator's working area. Finally, we can look at the inverse kinematic solver. A Jacobian pseudo-inverse solver was selected. The solver consists of a solver and a null space projection element. Breaking down the equation, the output is the joint velocities, JA dagger is the pseudo-inverse of the Jacobian matrix, XD dot is the desired velocity, K is just a basic gain, position error is calculated using the forward kinematics, there is the identity matrix and the joint limit objective Q.0. Q.0 is the null space projection. It uses extra redundancy of the robot to achieve a secondary objective. Shown is the objective chosen, which is to steer away from the manipulator's joint limits. Now we can take a look at the Matlab Simulink implementation. First, the forward kinematic script, the Jacobian matrix script. This is the pseudo-inverse solver, and this is the joint limit objective. This is the Simscape multi-body model of the robot arm. Shown here is the method of plotting coordinates in the simulation. Now we can run the simulation and solve the joint angles for the desired trajectory. The trajectory first waits 10 seconds to allow the solver to converge. Here the simulation is being sped up in post. The solved data is then outputted to the workspace. A custom data interpreter script is run to view the simulation results. The data interpreter script creates graphs for end effector position, joint angles, and 3-dimensional trajectory plots. A custom Arduino firmware was created to allow angles to be sent or received over serial, allowing a heavy solver to be run on desktop hardware. Shown here is the Simulink player sending angles to the real manipulator. As required for the project, a proportional integral controller was implemented into the Simulink player. Shown here is the controller diagram. The proportional integral controller massively improved the tracking accuracy of the manipulator by increasing the responsiveness with the proportional control and removing the steady state error with the integral controller. Proportional and integral gains were tuned using trial and error on a per joint basis. Further comparison scripts were created to allow different runs to be compared. Shown here is a comparison between a run with and without a feedback controller. This is shown both with a live video and the end effector camera tracked. It is also shown using a digital replayer script to play back the angles measured by the real robot inside Matlab Simscape. All of this would not have been possible without the modifications undertaken to the robot arm. Overall, the project was an enormous success, as inverse kinematic algorithms were successfully implemented onto the Arduino Braccio. Furthermore, closed-loop feedback algorithms were implemented to great results, allowing for massively more accurate tracking of a desired trajectory. All of the project files discussed today are available on GitHub and may become available at a later date. Thank you for watching, and I would like to say a massive thank you to both Dr. Umberto and George for all their help within this project.